In this session of work, energy and power, we are going to apply the concept of work kinetic energy theorem, and it's a very important application. We are going to find the maximum compression produced in the spring by the moving block. Now first of all, we are going to revise the concept of work kinetic energy theorem, and work kinetic energy theorem will be given by work done equal to final kinetic energy minus initial kinetic energy. This one is the work kinetic energy theorem, right? And that we have discussed in the previous sessions. Now we are going to revise the concept of work done by the spring force, and this concept was discussed in the previous session. The work done by the spring force, if this spring is extended from the position x1 to position x2, will be given by minus half k x2 square minus x1 square, right? This one is the problem that we are going to discuss. Block is moving with the speed u toward the spring, which is initially relaxed. In this problem, we have to find the maximum compression in the spring if this block M collides with the spring with the speed u on the frictionless surface. This problem will be solved by using the concept of work kinetic energy theorem. First of all, we have to apply the concept of work kinetic energy theorem. Total work done during the compression of the spring will be equal to change in kinetic energy of the block. As we know that the initial kinetic energy of the block will be half mu square, and at the maximum compression, the kinetic energy of the block will become 0. During the compression of the spring, the block will have three different forces. One is the normal reaction, one is the weight mg, and another one is the spring force. You have to find the work done by all these three forces, and then you have to take the algebraic sum of that work done, and after that work done will be equal to change in kinetic energy. This one is the approach for this problem. Now we are going to discuss this problem in detail. Now we are going to solve this problem, and in this problem a block of mass m moving with the speed u on a frictionless horizontal surface. It collides with the spring of spring constant k. We have to find the maximum compression in the spring, right? Now consider this block which is moving with the speed u toward the spring of spring constant k. It compresses the spring, and the maximum compression in the spring will be equal to x, right? And we have to find the value of x. As we know that at the maximum compression, the speed of the block will be 0, and hence the final kinetic energy will be equal to 0. What will be the approach of this problem? We have to apply the work kinetic energy theorem, and that will be equal to the work done equal to change in kinetic energy, right? And hence the work done will be equal to change in kinetic energy. That will be equal to final kinetic energy minus initial kinetic energy. The value of the final kinetic energy will be 0, and the initial kinetic energy will be equal to half mu square. Now we have to find the value of work done by the various forces acting on the block. The forces which are acting on this block will be the spring force during the compression, weight mg, and the normal reaction, right? Normal reaction and the weight mg. Now the work done by the normal reaction will be equal to 0, because the normal reaction and the displacement of the block is perpendicular to each other, right? Work done by the weight mg will also be equal to 0, because mg is vertical downward and the displacement is along the horizontal direction. That's why the work done by the weight mg will be equal to 0. Work done by the spring force will be given by minus half kx square, where k will be the spring constant and x will be the maximum compression. Now applying work energy theorem, you have to take the sum of all these three work done, that will come out minus half kx square, right? Total work done will be equal to minus half kx square. This total work done will be equal to change in kinetic energy will be minus half mu square. After very simple calculation, you can get the value of maximum compression, and the maximum compression will come out u root over m by k, that you can see, right? This is the problem that we have solved, and this one is very important problem.